Yeah, so second set of lectures today is by Samriddhi Shankar also from ICTS, and he'll give an introduction to turbulence.
Yeah, so thanks, Abhishek and Sanjib. So that's my name. You have my email address if you have any questions. And unlikely, but if the lectures make you sleepless with doubts and worries, you also have my phone number if you need to call me up and check. But I hope that that situation will not arise. The tutorials will be given by Ritik Mukherjee, who's somewhere there. Should be somewhere here. And he will sort of fill in some of the gaps in what I'm going to do, and I'll point out what are the gaps that he'll fill in. That's Ritik's email address. So the references, I mean, again, don't worry too much about it. At different parts of the lecture, I'll also point out other places that I'm sort of, building ideas from. But in general, there are 3 books which I think are very nice. They're by Frisch. They all have the name Turbulence somewhere, so I haven't tried to write the actual name of the book. So there's by Frisch. There's a book by Davidson, especially those of you who might be interested in things that are not going to cover in terms of vortex dynamics and real sort of fluid dynamics. You'll find that in Davidson. Lissier also is a very nice textbook for some more formal things. I'll also be sort of liberally using the content in these papers. Some of them are a little old, but one of them that I really like is Greg Ing's recent perspective article in JFM, which is again a very nice place to start. And finally, in case you want some sort of inspiration to try and learn the subject, but coming really from the masters. So there's a very nice article in Physics Today from 1990 by Steve Ozag and Uriel Frisch. Some of those ideas are perhaps dated now, but most of the things that I'm going to discuss over the next 4.5 days will, some of that excitement, I think, still suffice. Okay, so let me begin with the first part of this sort of 5-day lectures. And let me begin by sort of, is the handwriting too small for those at the back? So let me begin by asking or trying to ask this question of what is turbulence. So essentially, because the maths, I will certainly do it, but this might be stuff that if I write will again be very small. So essentially, what we'll sort of try to learn in this course is how to describe seemingly random motion of fluids. All right. So you can use other words, you can say random, you can say unpredictable. What other words have I used? You can say chaotic. And this typically happens to fluids such as the one we have in this room. Everywhere, flows are everywhere, right? There's air, water, etc. Typically, this set of sequence of characteristics for these flows, all of which we sort of term as turbulent flow, we'll make things more precise as we go along, is both ubiquitous, so you see it in nature, in industry, in experiments, and all of this seems to come out of situations where the viscosity of the flow is very small. Let me just write very small. Now, viscosity, of course, is a dimensional object, kinematic viscosity with dimensions of meters square per second. So something being very small, which is dimensional, often, what is small becomes an issue. So essentially, as we go along, we will see that we'll use this to construct a dimensionless number called the Reynolds number. And when that Reynolds number is very large, and this is perhaps something that all of you as undergrad or graduate students know, when the Reynolds number, which we'll define later, is very large, which is roughly the same statement as the above, flows tend to show these sort of behavior. And the reason why I sort of stress on the word seemingly is that, in fact, if it was completely random, unpredictable, and chaotic, to the extent that you cannot make any sort of statements or predictions, why are all of us here for the next 5 days? So we shall figure out why there might be patterns within this sort of framework of flows which are turbulent. So essentially, from a point of view of statistical physics, we are essentially dealing with a non-equilibrium driven dissipative system. Which more or less shows up in many natural settings and otherwise. So what we will sort of, so you will see elements of what we are going to learn over the next 5 days in areas such as, I don't know, astrophysics, for example, in understanding how solar. So on Friday, the last half an hour or so, I'll probably be discussing some of these sort of applications at different points. So you see them in areas of astrophysics, for example, if you were to understand solar flares, solar winds. These also seem to have properties, by and large, which we are going to discuss. In atmospheric sciences, of course, when you think about clouds and you go a few sort of hundreds of meters up there, the flow is very strong, so they're very large velocities. So they are in situations where the Reynolds number is very large, and one tries to understand what that means for little water droplets or ice crystals, depending on the latitude you're in or the height you're in, and what it means for those sort of things. Geophysics, I mean, the list you can sort of keep on adding. You can think about volcanic eruptions, and those typically throw up a whole bunch of little particles and ash, and you want to know what their dynamics is, because they're, again, moving around in a flow which is kind of random and chaotic, etc. Marine systems. Of course, in all sorts of engineering, etc., etc. Right? Good. So what's common to all of these systems? What's common is the following. First, of course, we need to describe the phenomena, and we'll get to those equations today itself, in terms of some velocity field, which is given at point x and time t, right? And this velocity field essentially will fluctuate like crazy. So for example, if I look at this velocity field as a function of time and space, the x-axis really doesn't matter. It could be space or time. You would probably have things which are all very jagged. And when you look at it in x and t, you will see fluctuations on various length scales. Don't get too perturbed right now. These are things that we'll formalize before we are done for the day. And so essentially, these flows are characterized by a wide range of length and time scales. And we shall see that this is something which makes life somewhat difficult as we use more standard theories of things. We shall also say that while this animal is strongly fluctuating and is unpredictable, but the averages make sense. So I can still speak about, and we'll again sort of make this more formal, I can still speak about a time average velocity field or a time average square of the velocity field. I can still talk about the energy of a system. Now, that energy that I measure right now might be 127, and a minute later it might be 130. A few minutes later it might come down to 120. So there are fluctuations. But if I wait for long enough time windows, in principle, I should be able to talk about things in terms of averages. All right. So these are the sort of things that we are going to So what that also means is because of these fluctuations, we will try to develop essentially what would be a statistical theory or a probabilistic theory. We can speak in terms of probabilities, and we will speak in terms of averages constructed thereof. All right. So the final bit of introduction to what will go on for the rest of this course, by the way, just stop and ask me questions when you want, is the following. So in our search for a theory, we will make certain simplifying assumptions as we go forward. These will be used tomorrow much more than today. One would be, we would deal with things which are homogeneous and isotropic, at least in a statistical sense. So as far as my flow is concerned, isotropy means that I really don't care if I'm looking in that direction or in this direction. Individual realizations, they will be different because everything is fluctuating. But if I look in this direction and take averages for 20 minutes, let's say, and if I look in this direction and take averages for 20 minutes, I should come up with the same number. So statistically, you have the system will be isotropic and homogeneous. We shall also not worry about boundaries. Essentially, what that will mean is, suppose I'm looking at a turbulent flow in a wind tunnel, or I sort of cook it up in this room, I'm going to essentially try and understand the physics of the flow, let's say somewhere in the middle of the room. Because then it will not really be affected by how the shape of, the geometry of the walls are, exactly where the ridges are, where the inlets are, etc. All right. So as we try to look for certain universal sort of ideas or results in this business, it's useful to forget about boundaries and to sort of take that out of the equation, as it were. This, in some sense, you will see later, corresponds to what physicists love using, which is known as periodic boundary conditions. Or in other words, you imagine that you have an infinite expansion, an infinite expanse, sorry, not expansion, quite different things, an infinite expanse of the fluid, and you're really not going to care about as long as the velocity, energy, etc., decay sufficiently fast and far away. And we will essentially deal with the idea of a non-equilibrium. Okay. So in these lectures, we will not cover several different important aspects of turbulence, and maybe, in the interest of time, I'll sort of park that thought later till Friday. But let's sort of begin at the very beginning, which is, how do I think about the velocity field at position x and time t, right? Any questions, by the way, on this sort of whirlwind simplistic definition of? They could be over time, they could be over space. We'll make precise as we go along. Okay. So for example, I can calculate the mean energy in my flow, and I can keep on calculating as a function of time. And what I will see are fluctuations, because they're not going to be in equilibrium. But if I average over reasonably large time windows, and we'll try and guesstimate what those time windows could be, I'll end up with the same number. So the averages make sense. Or I could play a reverse game in sort of statistically stationary state, is I can look at the mean density of energy, which is something divided by the whole volume, and I can measure things here and here and here and here. So each of these measurements will have different values, but on average, I will find that they're all good. Never mind. The first thing we need to worry about is how do I write down an equation for the velocity field u at x comma at position x and time t. So what we do is essentially we can consider some blob of fluid with volume delta v and density rho, which in so I really should do something about my handwriting. I'll try. All right. So this blob of fluid, which is freely moving, so I can write down Newton's second. So what I'm essentially going to use is Newton's second law. Right. So the force acting on this guy, in the fluid, there's some pressure. So if this is a volume element with surface element S, I can trivially sort of write down that's my mass, rho delta V, which will essentially be nothing but the pressure integrated over the surface. I can take the divergence theorem and essentially write this as. All right. All of you with me? Yeah. If you're worried, this is coming from the fact that the force acting on it will just be. And then I take the divergence theorem. Right. In an ideal fluid, this is all that there is to it, all right? And this gives rise to what's known as the Euler equation once I expand the convective derivative term out. However, in real fluids, you have other forms of stress, and those other forms of stress comes from the fact that a real fluid could be honey, oil, water, air, etc., etc. So there has to be some intrinsic property of the fluid. As we all know, honey flows less slowly, more slowly than water. Water flows more slowly than air, etc. So there must be some other term acting on the equation of motion, which comes from the fact that you have viscosity. So what we'll try to figure out in the next few minutes is how do we incorporate the idea of viscosity in the equation of motion for u at x comma t. All right. So all of you are on board. What is it that we want to achieve? Right. Great. Yes, sir. Yes. Yeah. So your question is, are things ergodic? Yes. So there are situations when it's in stationary regime for certain quantities, that's completely valid. For freely expanding or decaying systems, that's not going to be true. So we'll make this idea of when we introduce angular brackets in the problem, we'll make this idea precise. All right. So how do I calculate forces due to viscosity? So what we'll do is the following simplification. So let's consider a rectangular fluid element, which has dimensions delta z. It's a small volume element, delta V, where all right. So this fluid element will have several shear stresses and normal stresses. So if this is the sort of cuboid that I've drawn, this is more a cuboid than a cube, then I will have stresses which act parallel to the surfaces and stresses which are normal to the surfaces, right? So with this notation, if we set up our axes, so I'll probably do one. So on this face, for example, you will have stresses which are shearing, and use a different color chalk. And stresses which are going to be normal to the surface, right? Similarly here, you will have normal stresses which go as Txx, let's say, and similarly, you can have, as we discussed, shear stresses on the surface of this cube, all right? So what we are going to do is try to understand the effect of this shear on this volume element and how it leads to distortions. Right? So if there is a net imbalance of all the stresses that you can draw on the three faces, then this cube that I've drawn will either deform or it will translate, right? So what we are going to try and do is to try and understand exactly how that deformation can take place. So let's look at one direction. If I look at the x direction, so this is unit direction x, I can effectively calculate the force which is along the x direction, right? So I can write this as the difference of the stresses, all of which are pointing to the x direction, along the x direction. So what do I have? I have Txx, which is pulling me on the x direction. Then I have a shearing stress which is coming on this wall and a shearing stress which is coming on the top wall. Is that clear? Yeah. So what I can do is I can calculate okay, where delta Tx, Tij are just the differences between the two walls here and the other side. Is this clear? Okay. So you can sort of go ahead and play with this, and you will see immediately the following. This, let's look at one particular term, right? So let's look at this term. So this term will be nothing but the gradient. So I should have multiplied by the separation, right? So how is Tzx changing over a distance delta z? Similarly, you can compute the difference on opposite walls of the normal and the other shear stress. And you will see something very nice which comes out. You will see that this surface area element picks up delta x, delta y, which then gets multiplied by delta z. You have the same form everywhere. And so this contribution essentially gives me right? But now I can calculate this force in all the other directions, x, y, and z. And so when the reasonably when the dust settles, I should be able to write this as so this is how far Newton's second law will get me, right? So I can put this in, plug it in here, and so the viscous forces will be something like the jth component. But I still don't know what this is. So I still need to calculate what my stresses are, TIJs, just to be able to close this form of equation. So what we are going to do is something simple, but this can be generalized for more complicated geometries. All right. We have two things at our disposal. We have mass conservation, which is a statement of incompressibility. And we will consider essentially Newtonian fluids, which will have a simple relation, as we shall see, in the calculation of the stress tensor. So let's look at a simple example where we can calculate this. Let's consider what's known as a shear flow. Where the velocity profile has the following feature. This is x, y. This is my velocity. So my velocity will just be ux, which is a function of y, 0, 0. So I'll do the most trivial example to fix the stress tensors. The more complicated general form, you will do it in the evening when you're bored, right? So I'll do it in 1D and 2D, which is something I can draw and calculate. Right? So what this essentially means is if I take any volume fluid element here, it's just a plane, which at T0, let's say is here, then at some T0 plus delta T, it takes on this shape. And this shape it takes on because there has been a shearing stress. So I take a fluid. So here's a flow, which only has ux, and the component. So this is 3D. So this is in the x direction. So there is only the x component of the velocity field, which depends on y. So I take a little plate, which I've done here. Now, because the velocity has this very nice form, has this very nice shape, in time, this box of chocolates would have been nicer, this box of chalk will start to deform because there's a smaller velocity here and the larger velocity here. So that's what I'm actually doing. Okay. And so essentially, let's say it has distorted by an angle theta at any point in time. Right. So what we want to calculate then is the rate of sliding. And that rate will be proportional to the rate of change in theta itself, right? If I shear more strongly, then d theta dt will be large. If I shear less strongly, d theta dt will be small. If I don't shear at all, d theta dt will be 0. So what we can certainly say in this example is Tyx, the shear stress Yx, will be proportional to d theta. But now we are in business, right? Because we know exactly what d theta dt is, because it's incremental. How do we know that? Any suggestions? We know exactly what this element is, right? No? How do we calculate d theta dt? Exactly by arc length. So perfect, great. So you know, for example, what is ux here at t0. Ux here will be just the same as this with the gradient of del u del x, delta x, right? And so what you can, so essentially this distance, I'll use another color, sure. This distance will just be ux delta t, right? And this distance here will be okay, everyone with me? Yeah. So I can just subtract out these two distances to get the arc length, right? And then I can take delta t going to 0, and I get a derivative form of this. So once the dust settles, what we can see is for that particular problem, t yx is proportional to del u del x del y, and that proportionality constant I can take to be some coefficient mu. We will later associate this mu with the bulk viscosity of the system, something which will distinguish air and honey. So this you can do more generally. In the interest of time, I'll just sort of won't go through how you make this construction in higher dimensions, but you can certainly think about this distortion where you have both other components of the velocity, and essentially you come up with this result in a general tensor form. So when you put it all back together and you cancel out delta v's on both sides, you essentially have this is the Navier-Stokes equation. And solutions of this equation will be the subject of our lectures. You can do a little bit more, actually. You can do one. The first thing you can do is divide everything by rho. When you divide that, you end up with a rho here, and you write this as some bulk viscosity by density. That's known as kinematic viscosity. That's a more useful way of thinking about it. And this you can also write using chain rule. Okay. So what we are going to do from tomorrow, today we'll do a little more groundwork, is to understand solutions of this equation when either viscosity goes to 0, or more usually what we'll do is we'll construct a non-dimensional number called the Reynolds number, which will just be the ratio of the nonlinear to the viscous term, which will tell me which term dominates in my problem. Is it the nonlinear term which dominates, or just the viscous term? Then you're reduced to a nice problem that all of you know in terms of diffusion equation. Right? And so the nonlinear, you can just do a dimensional analysis, and that's good enough. In the nonlinear term, you have 2 powers of u, 1 power of inverse length. In the viscous term, you have 1 u, 1 viscosity, 1 length over squared. Okay, so put that all back together, and this will be some length, some velocity, some viscosity. And what we'll study is essentially the solution of the Navier-Stokes when that non-dimensional number becomes very, very large. Okay. We will see this later more formally, but just so that you don't end up with expectations that you shouldn't have, unlike critical phenomena, we will not be able to prove a critical Reynolds sum in this problem. So most of it will be in the asymptotic limit of Reynolds going to infinity. Okay. By the way, I strongly urge, because I had to skip it because I suddenly realized I'm sort of running pretty late. I strongly sort of recommend that you do this calculation, which I just did in 1D for higher dimensions, and convince yourself that indeed this constitutive relation is correct, right? That the stress tensor is indeed proportional to the Laplacian of u, and the proportionality constant is what we call bulk viscosity. One final remark on this, and that's the following. You see, this will be coupled with divergence u. So this will essentially form the basis of incompressible hydrodynamic turbulence. The incompressibility constraint, the momentum equation, and the fact that we look at solutions when Reynolds goes to infinity. 2 further remarks. One is you immediately see that you're dealing with 4 variables, ux, uy, uz, and a pressure which is scalar p. So you have 4 variables. And the reason why this is a complete set of equations is that you get 3 equations out of here, and you will get the last one here from the divergence u equal to 0. That actually is very interesting. So what I will again ask you all to do, work this out at home. I'll just sort of write the result as it were. You can actually take the divergence of the Navier-Stokes equation itself. So hit the equation with a divergence. And what you'll see is this term will vanish, this term will remain, this term will vanish, because the divergence will commute with the Laplacian. All right, and this will essentially give you a Poisson equation. What you will see is the following. you will see that the pressure field at x can be rewritten in terms of this integral over all other points x prime. And this is something which makes the problem essentially non-local. Right? Any questions on the derivation of the Navier-Stokes before we want to do two other things today before lunch. One is to understand what's the effect of nonlinearity beyond making things non-local in that way. And we want to understand how to sort of think about chaos for deterministic systems, because right here we have no noise, there is no forcing, nothing. I can add a forcing, but there is no inherent stochasticity in this problem. So while I erase things, just let me know if you have a quick question. Okay. Let's look at some properties in this part of the Navier-Stokes equation. Taken unit density just to simplify my life, but there is a density sitting somewhere. So this equation sort of obeys several symmetries. I won't go through all of them. So in principle, this obeys a form of Galilean invariance, so space translation. So you take essentially x to some x plus r, where and t goes to t and u goes to u. So many of these symmetries the Navier-Stokes obeys. The one symmetry that I would like to sort of comment on is essentially what happens to scaling. So you guys can sort of go back and look at space translation, time translation, parity, et cetera, and see that all of those are the Navier-Stokes equation obeys them. Yes. Very good. So in case of turbulence, these symmetries are all restored again in a statistical sense, all right? And those will be things that we'll do from next class. So for example, if you see flow past, if you're crossing the river on the train and you'll see flow past the sort of pillars of these rivers, you would think that there is a symmetry broken on the left and the right, just a little away from the pillar, so you're not seeing the pillar. But statistically, you will see those symmetries are again all restored. Good question, thank you. So what we'll do is, let's look at one example of this, because this is going to be really useful for us. So how does the Navier-Stokes equation transform for the scaling group H? This notation, sorry, I should have mentioned, this sort of stylized R stands for real, so lambda belongs to positive real, and H, the scaling exponent, is just going to be a real number. So this scaling is something which really makes life very interesting if you're looking at scaling transformations and scaling laws in Navier-Stokes. So if you put all of this back in the equation, and I'm sure you guys can do it very quickly, you will notice the following, that for mu not equal to 0, finite, you will pick up a unique scaling exponent of -1. The interesting thing happens for viscosity going to 0, or we can assume viscosity being very, 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 very small. You will see that this property sort of shows up in a kind of miraculous way on Wednesday and Thursday, depending on the pace at which we go, when we try and understand the scaling properties in turbulence. Okay. So this is something that you should be able to check in a minute. All right. So now let's define the first definition of what we will mean by angular brackets. And later we might change them depending on the specific sort of calculation that we are doing. So what we will, so I'm just setting up the machinery of things that we are going to use, all right? Definitions and notation. So let's assume a function, any function f of r, some arbitrary periodic function. So I can define averages for this periodic function in terms of 1 over L cube in some box of size L. Right? From this definition, certain things follow. And again, it's just sort of essentially benign algebra that you can do and check. I'll just skip going through it. Is the following. You can show that this will be 0 because some of these results I'll use in a couple of minutes from now when I look at conservation laws. We've looked at scaling. We want to look at conservation laws just for completeness. Some other function g, which has the same property. That's all I will actually need. So when you look at solutions of Navier-Stokes using periodic functions of velocity, sorry, Abhishek. The second one? Yeah? There are derivatives in both. So I can do an integration by parts and I can break this up. So I take this guy, my average is defined in the sense here. I'll do an integral of this, and so that integral I can then do integration by parts, and the surface term will vanish because of the same reason as here, and so you'll get this. Huh? Oh, sorry, yeah, sorry. Okay. Fine. So what we are able to see are the following conservation laws. I'm actually not going to prove this. You can show that momentum is conserved. This is energy conservation. This is essentially the curl of the velocity, which I write in like a vortex. So you would assume that in the limit of viscosity going to 0, this term goes to 0, and the total kinetic energy is conserved. Curl of the velocity. It's the same as. Okay. Now, hopefully at the end of this week, you will start to develop some appreciation that this statement, which seems trivially true, that in the limit where viscosity goes to 0, as physicists, something going to 0 multiplied by something positive definite should vanish, may not be exactly true. What we will learn to appreciate is that these gradients may actually end up going to infinity faster than viscosity going to 0, and essentially, even in the limit of viscosity going to 0, the right-hand side of this equation may not vanish. So that's something that hopefully by Friday we'll have some appreciation of. But in general, if you don't sort of worry about such unpleasant surprises, this is something that you would think of. There are, of course, other things which also go to Z. You can also show conservation. So in case you guys want to worry about these things at the end of these lectures, you can think about helicity, which has also will be some viscosity times some object there. Okay. So in general, the conservation law for Navier-Stokes is written in the following way. So all I'm going to do, just to look at the global conservation laws, which we already wrote down there by just using identities that I had written down, or we can take the following point of view. I can take the dot product with u of this equation. So the first term will just give me ddt of the total kinetic energy, half u squared. Volume integral, you will see that this term will drop out of the equation, and you're only going to be left with the viscous term. So what we can show, these are things that we will do more systematically when we So I've just rewritten this in some other form. And I will call this quantity as epsilon. So all that it's saying is essentially a statement of conservation of energy, that the rate at which you lose kinetic energy is completely governed by viscous dissipation. And typically, I will use the symbol epsilon for that. And again, just to re-emphasize the point, if things are smooth, so all these derivatives, etc., exist and nice and well behaved, then certainly in the limit of vanishing viscosity, or for the Euler equation where viscosity is 0, the time rate of change of kinetic energy must be equal to 0, which would mean that the kinetic energy is constant. All right. Okay. So the embarrassing or the curious thing right now, you could argue that the nonlinearity played no role in this whole game, right? Because once I took the box average, etc., the nonlinearity vanished. You reduce it to surface terms. You assume either periodic boundary conditions on the velocity field or the velocity field decays sufficiently quickly at the boundaries. And you see that the nonlinearity has no role to play as far as conservation is concerned. So what is the role of nonlinearity in all of this? So the role of nonlinearity is actually quite interesting, and there will be many instances when we'll come to the role of nonlinearity. But let me make the following argument once. So let's assume that, well, not assume, we already discussed that the velocity field or the turbulent velocity field is going to be multiscale, right? So what I can do is essentially I can use a filtering. So I can take some cutoff. So let me sort of write it down. All of you are familiar with Fourier transforms, right? Great. So I can directly write it in Fourier space. I take my velocity signal, I choose a reference wave number, which I write as capital K, and I'm going to filter my signal above and below these wave numbers. I reconstruct two signals, and of course, by definition, so essentially, let's say if I have some, what such filters do is if I have some function like this, but which also has things which are happening on short and large frequencies, by applying that filter, I can either generate a signal which is just the short frequency stuff, or I can generate the signal which is the long frequency stuff. All right? So that if you replace F with U, the Navier-Stokes velocity field, and actually apply it here, you will be able to write down the velocity field for the lessers and the smallers, and you will see, I mean, this is something we'll see later in a more sort of systematic theoretical way, but this is just to give you a sense of what nonlinearity does for you. What you will see is that the role of nonlinearity essentially is just the transfer of energy from small wave numbers to larger wave numbers, right? And so if you essentially integrate over all wave numbers, which is roughly what we did there to get conservation laws, then everything that the nonlinearity did washes out, because its role essentially was transferring from wave number 10 to wave number 20 to wave number 30, the kinetic energy that it had. Okay. Questions? I'm sort of not doing this full calculation in the interest of time, because I want to cover one last aspect that we'll need to look at turbulence today. But do you have any questions now at this stage? Okay, good. So what do we have? What have we done so far? So far what we've done is we've derived an equation, a hydrodynamic equation, which is somewhat valid, which is valid at length scales much larger than, let's say, a few mean free paths of the molecules which compose this fluid. So this is a hydrodynamic description, which is likely to break down if you're going to scales which are mean free path. And we came up with a nonlinear evolution equation, and that's called the Navier-Stokes equation. We looked at the conservation laws that these equations satisfies, and we saw that for global conservation, but I should have used the word global there, for global conservation, we really don't care much about what the nonlinearity does. But all along, we've talked about the importance of nonlinearity in turbulence and the fact that in the Reynolds going to infinity limit, it's the nonlinearity which dominates. So the next thing that we saw was that the role of the nonlinearity was essentially just to transfer energy from large scales to small scales, or from smaller Fourier wave modes to larger Fourier modes. And one way to do it, which I didn't do out of sheer sort of time and laziness, is if you sort of split your velocity field into high pass and low pass filters, and you write down the Navier-Stokes equation in terms of those, you'll end up with about 4 terms in the nonlinear. The nonlinearity will split into 4 terms. The lessers, the greaters all interacting. You'll see some of those vanish. And eventually what will be left will show you that it's only the small wave numbers which are pumping in energy on the large wave numbers. Yes, you had a question. In the total, so that we will look at the transfer rate a little later, but here, relatively speaking, what you will see from there is not the participation as such, but if you calculate the energy flow, all you will see is from small wave numbers, the energy is going to large wave numbers. Right? Okay. I mean, there's something peculiar here, which we'll probably not discuss in this course at all, but if I understand your question correctly also, is that if you look at all the wave numbers which will contribute to the nonlinearity, typically you see much more contribution from wave numbers which are roughly of the same order. And that allows certain mathematical juggleries to happen. But that's more an empirical fact than anything else. Okay, so the last ingredient we need to build up our story next, in the next class, is chaos. So how do we understand how equations which are completely deterministic end up showing solutions which are chaotic? Right? So in the last half an hour, what we'll do is try and understand that. Okay, so let's begin with a simple idea in a deterministic system. So what we'll do is actually do something that Akshit had introduced in his lecture this morning. So we'll begin with something which is discrete. So we'll have a variable x, whose n plus 1th avatar is a function of what it was the previous step. All right. So for example, I can take this to be cosine of xn, and you can solve this problem iteratively, and you'll find that as n becomes very large, and it depends from what initial value of x you had, you will essentially reach a fixed point of all right. Have all of you seen such things? Sorry. Yes? No, sorry, are you familiar with, I mean, because some of it was also taught last week and also Akshit was discussing this. So you all have seen this, right? How to construct these solutions iteratively on a graph, etc., right? So the interesting one goes back to something that Akshit mentioned today. I'll use it for a second just to illustrate something. And so what I'll have is xn plus 1 okay. So all of you know what the solution of this is. You all saw this about 1.5 hours ago in Akshit's course variant of this. So when a is less than 1, xn goes to 0 for large n. Yes? You know how to calculate the fixed points, right? So if it's a complete fixed point, then you'd say xn and xn plus 1 both are some number x star, and you solve the quadratic, and you'll find this to be the solution for a less than 1, right? Whereas for a, as you change this parameter a and you push it up beyond 1, you'd see very interesting behavior, which has to do with things like bifurcations, period doubling, and eventually chaotic systems, right? So the solution for some values of a will be completely undetermined. And it can oscillate all over the place depending on when you measure it, whether you measure it at n equal to 100 or 140. Right? So Ritik will sort of show a bit more about this in the evening. So I will sort of not go through the full process of this. But what I will do is I would like to sort of end by showing you a model of chaos which we'll derive together. And let me first show you how the experiment runs, and then we'll work it out on the blackboard together, okay? It's an experiment that we can do here ourselves. So I strongly encourage you all to do it, try this experiment, but not anywhere near my office or this lecture hall. It can get a bit messy. Connected, right? Okay, so watch carefully because we'll construct the solution of this and it'll lead to the more fundamental equation in chaos. So that's a wheel. You see those cups there? And there's a water spout. Now those cups are leaking. So some of the water is falling down. And what you see is if you look at that wheel, you see the motion is completely chaotic, whatever our perception of chaos is. The direction of rotation keeps on changing as well as the speed. Okay. So just keep in mind this geometry, and we'll try and derive some continuum equations for this, which will lead us to something which is perhaps the most well-known equation in sort of theory. None, as far as I can tell. I think it's just to keep alternate colors or just to help to, yeah. Because even if there is a difference in terms of how quickly it leaks, that's bad news for me because I'll assume that to be constant. Okay, so let's worry about trying to understand this equation together. So all of you have seen it, you will remember exactly what we saw. Let's try to derive an equation for this. Okay, so I think we have seen enough. So essentially what we had was the following. Essentially had a wheel like this, where there was a flow of water from the top. At any instant, let's say, this is how I'll measure the angle. And I had all these cups here. So what mattered for us was the following. If I'm going to write down an equation of how this rotates, I need certain parameters in the problem, right? So the first thing that I can think of essentially is in this arc, how do I measure angle? So am I here or here or here is given by theta. At the end of the day, I want to measure the angular velocity, which we saw was a function of time. I want to measure the mass density, let's say. I want to measure what else? So these are probably, we'll add to this list if we need more while constructing the equations of motion. The reason I'm going through this is it actually takes you somewhere close to turbulence, not really, but essentially to drive home the idea that without anything else, nonlinearity is often good enough to make things chaotic. All right, you don't need to invoke too many other things. So essentially, if I just look at some arc length, let's say defined as theta 1, theta 2, the mass contained in this arc length will at time t all right. So I need to understand what's the change in mass in time delta t. So I'm sitting here, and remember the movie that we saw? I'm watching the wheel move. I fixed a θ1 and θ2, and I'm going to look at that arc, and I'm going to see the change in mass of water there. Let's imagine the cups don't have any mass. Even if it did, it doesn't matter. I'm going to look at the change in mass from delta m in time dt. Right? So this essentially would be water which was pumped in, water which was leaked, and as the system rotates, let's say at this time instant, I assume it's going in the following way, then the amount of water which came in because of rotation and the amount of water which I saw got lost from my field of vision. All right? So all right. So this would mean that delta M would be delta T coming in from the fact that there's an inflow which is dependent on the amount of water I'm going to leak. That's my leakage rate. So that will be Km, kappa K. Rest coming in from the fact that my arc has moved in delta T by a distance omega delta T. Right. So now I can divide everywhere by delta T and take the limit All of you with me? M is something I don't know. Actually, I don't care because I'm going to work with mass densities. So this I can replace as the change in time of small m and integrated over the arc length θ1 to θ2. Right? This was the definition of m anyway, because just one sec, because m. Yes. Where? Oh, that's because the leakage rate, the rate is not a function of theta, but m is. It's the rate, so the amount of leakage depends on how much m you have, and that proportionality constant I said k. So that's what I mentioned when he was asking me about the colors of the cups. So in principle, I could have a k function, but either way, the cups would turn and come back, so it wouldn't matter. Okay, fine. So then I can erase this. So then when the dust settles, so I will put this, I will replace this here, and then I don't have to worry about which theta1 to theta2 interval I'm taking. So I can equate the two integrands in this equation. And so I will end up with okay, so that would be my first equation, some sort of an equation, some sort of a continuity equation, right? But this is no good, right? I don't know M, how M is distributed. I need to know omega. The rest, let's say I still have. I mean, Q is depends on how I set up my tap, etc. So I need one more equation. And the second equation that I need can come from Newton's laws, as usual. Under the assumption, and this is an assumption really, that my moment of inertia is constant in time, right? Given that there's water splashing around and the M is changing, etc. My moment of inertia in principle should change. But let's assume that my moment of inertia is constant. So what I will end up getting is that's the term I didn't write here. So some sort of one more parameter in the problem. Let's call this T. So with that same sort of picture that we have there, where I'm looking at this arc here, gravity is downstairs, is pointing downwards. What you can show easily is that the infinitesimal torque acting on this will be essentially mgr sine theta, where mgr is the mass. And md theta will be the total mass in this. All right? So this would mean that the other equation I need to worry about has the following form. Okay. Equation 1 and equation 2. So this is a bunch of coupled partial differential equation whose sort of solutions in principle describes the water wheel, the chaotic water wheel, whose video we saw completely with the mild assumption that the moment of inertia is constant. So how do we solve this? That's the question. So the way we solve this is the following. So if you remember, it's all here. Remember that this is a periodic system as far as the mass of the water is concerned. So I can think about small m and expand it. When I think about periodic functions, I'm going to expand it in a Fourier basis. Q is also a periodic function necessarily, but I can make even more simplifications on Q, as we shall see in a second. So what I can do is I can expand mass in the Fourier basis. So M, keep track of size. All right. So I can expand this to equations in this Fourier basis, and then I'll get a horrible looking object, which we can. Okay. Yes. Yes. That's why it's metric. Of course, at other places, as you were seeing, because of the leakage, you'll still have Qs. So I'm not going to use Q as a delta function. The inflow here is at the top, but there will be added effects because of the leakage in the other terms. Yes. So it is. So this would be more like a drag. So my I omega dot is proportional to minus omega. Let's say lubrication in the spokes of this wheel, etc. All right. So what we can. So what we can do is we can play the usual game of equating coefficients of sine n theta, cos n theta, look at orthogonality, all of that, and you will find a nice equation. So I'm not going to work it out. I'm running over time, but you can do the same, put in the same expansion in the equation for torque, and you will get but you see something interesting there. What you see is in that torque equation, just have the A1 coefficient. The other coefficients vanish because of orthogonality that you will see when you do this. So what you end up having is just with the 1th terms, you end up having a closed system of equations. The A1s and the B1s separate out. And so you can write this and what you will see in the tutorial today is that this is exactly the same as what's known as the Lorentz equations. Lorentz sort of derived it in the context of convection, and you can think in terms of Rayleigh numbers, etc., to show when these systems become chaotic. But you can actually sort of, you can actually sort of go through these equations quite systematically and see that there are fixed points indeed when certain combination of these parameters are small or large. And one of the fixed points indeed is no rotation. It may not be a stable fixed point, but it is a fixed point. Think about setting up the chaotic water wheel with empty cups. You've just turned on the tap a little. Of course, it won't move. So you can get all those solutions from this. But most importantly for me, this reduces essentially to the Lorentz equations, which is sort of prototype chaotic systems. Abhishek, can I just take 5 more minutes? And okay. I wanted to discuss a little bit the Lorentz equation, but I think we'll just leave it for the tutorials. And you will see exactly what these trajectories look like. But maybe I'll just end today with essentially talking a little bit about these trajectories when things are chaotic and what makes them interesting. And Ritik will sort of look at these more. Yeah. Yes. Which term? Which term, sorry? Yes. But the containers are also leaking in different ways. So eventually the mass distribution. Well, even if it isn't, but you still have Q. So one of the containers has come to the top, and so the mass will keep on changing, right? So it will all be dynamically evolving. Yeah, I've of course assumed K to be constant, and it's the same everywhere. You're right, but I still have an inflow. And the fact that it's leaking, it's going up, so the other cup sort of drips in, etc. Okay. So there are, would you be showing phase space contraction in the tutorial at all? Okay, so I'm just thinking. Okay. Let's just discuss. Let's just discuss a definition of chaos. And again, watch out for the tutorial. So what I'll do is I'll just define it for you, and then I'll worry about the different elements of this definition as and when required. Okay, this is aperiodic as opposed to aperiodic, right? let's define each of these. So this would mean that trajectories do not settle to a fixed point. So often what you will encounter are objects on Thursday or whatever, objects called attractors, strange attractors, where all these trajectories, and you'll see examples of that in Ritik's tutorial, where all these trajectories are sort of moving around, but they're never sort of settling in one fixed point. So they're sort of around a basin of attraction. And what you will also see, or you can do this yourself, is you will find that the volume on which it sort of settles down these attractors, that volume shrinks exponentially, but the area of that thing grows unbounded. And that's very easy to see in the Lorentz system, which we just derived using the chaotic water wheel thing. The second thing, of course, is that we've discussed at length, is the fact that we are able to see this in deterministic systems. So we do not need any stochastic or noisy input to drive a system to chaos. All we needed was nonlinearity, and that's good enough. So the Navier-Stokes in principle should have solutions when the nonlinearity is strong enough compared to dissipation for it to show chaotic behavior. And the last thing is this, which is known as sensitive dependence on initial conditions. So this goes by the name Lyapunov exponent. And essentially, what you can show is the following. So you can think about any trajectory where you have a second trajectory which starts very close to each other, but slowly it tends to diverge, right? That's trajectory 2, that's trajectory 1. And the rate of divergence, this gap that you have here, let's call that gap at any point delta, that gap would grow as the initial separation with exponential lambda t, where lambda is the Lyapunov exponent, right? Where this was its initial gap. This actually makes, and this is a final remark to make you all feel slightly depressed about things, is the following, is that you can argue that for chaotic systems, or for any systems, your collaborator or mentor would sort of tell you to make initial conditions more precise, and you can sort of get better results. But if you have chaotic systems which diverge, then you can go back and convince yourself that because of this exponential dependence, even if you, let's say, improve or reduce the initial uncertainty by several orders of magnitude, you gain very little in terms of how long your system will be predictable. So that's something that we'll come back. So this is really at the heart of the unpredictability of nonlinear chaotic systems. Okay, so I will stop here. I'm sorry for overshooting a little. And so we have set up all the tools we need. So from tomorrow, we'll go back to Turbulence and we'll use some of these ideas to understand. Thank you.